we need to see a couple of things regarding matrices. So we say one matrix, but two matrices, three matrices. So formal definition, just to make sure everybody's on the same page, a matrix is a rectangular array of numbers. So what we have in a matrix are numbers. And those numbers, we give them a special name, entries. So that's what we call entries of a matrix. Another important thing for a matrix is a size. What is a size? Well, it is number of rows, so how many rows we have, by a number of columns. So columns are standing. So if I have a matrix that has 3 rows and 7 columns, I'll say that the size of the matrix is 3 by 7. In general, this is how we note matrix entries. They have indices, so the first index is for the row and the second for the column. So you see the row 1, everybody in the row 1, the first index is 1. And as you move the second index, here is the column 1, then column 2, then column 3, column 4, till the column n. And then we go for the row 2, the first index is 2 for everybody in the row 2, and then the first guy is 2, 1, because it's the row 2 and column 1, then A2, 2, so row 2, column 2, row 2, column 3, etc. until row 2, column n. I specify here the size m by n, so m rows, n columns. We don't need to do it all the time. At the beginning it will be useful, later on we are going to get used to it. Another notation that is important is how do we find an entry from a matrix. So this notation here says matrix A, entry 2, 3. What does it mean? Is the entry in A that is at the row 2 and column 3. So entry in row 2 and column 3 of matrix A. A42 is the entry, so the number that is at the row 4 and column 2 of matrix A. So that's the just notation. Another important definition is equality of matrices. How do we know that two matrices are equal? Here's the definition, and it's super important. So matrix A and B are equal if and only if two conditions. Matrix A and B have the same size, so they have the same number of rows and columns to each other, and also the corresponding entries are equal. Okay? So that means, for instance, in this example, I have two matrices A and B. Both of them are 2 by 2, so 2 rows, 2 columns. And so that's the first part of the definition. That's good. We have same size, 2 by 2 and 2 by 2. Good. Or when I write it, 2 by 2, 2 by 2. Great. But there's another part of the condition that says all the entries in corresponding positions need to be equal. So entry 1, 1 from A is the same as entry 1, 1 from B. Entry 2, 1 from A is the same as the entry 2, 1 from B. Entry 2, 2 from A is equal to entry 2, 2 from B. But entry 1, 2 from A, which is 1, and entry 1, 2 of B, which is 0, they are not equal. So the matrices A and B are not equal because the entry 1, 2 of A is different from the entry 1, 2 of B, even though they have the same size. Okay? So equality of matrices requires two conditions. First one is on the size of the matrices, so they must have the same size. And then second one is that the entries at the corresponding positions need to be equal. For instance, here I have a matrix A, which is containing 2, 1, and 0, so this one is 3 by 1, so 3 rows, 1 column. And I have matrix B, which is containing also 2, 1, and 0, but in a different order. This one is 1 by 3. So you see the size is different, even though the content is the same, if you wish. So the numbers that are inside are 2, 1, and 0, but the size of matrix A is 3 by 1, and size of matrix B is 1 by 3, so the size is different, therefore matrices are different. Okay, very important. Size is super important thing. Another common error is when we deal with matrices that are 1 by 1. So this is a matrix 1 by 1 containing number 2 inside. While this matrix is different from a number 2 because this A is a matrix of size 1 by 1. While this guy here is just a number. So they belong to two different species. It's like birds and donkeys, completely different. So never confund the number with the matrix. Those are two different species. Be careful. Another example of the difference is matrix C here, which is 2 by 3. So it has 2 rows and 3 columns. Obviously, since the size is different, with A and C are different. Even though when you check the values, you have 2, 1, 3, 1, and then 0, 2. So the parts of matrix A are all here, but there are some extra things. We don't care. What matters is first thing the size. If the size is not the same, goodbye, matrices are not equal. So A and C are different, so they're not equal because they have different size. The same thing goes for B and C. B was 2 by 2 and C is 2 by 3. So they are different because the size is different. So as soon as size is different, we know the matrices are different. If size is the same, well, we need to check the entries in that case. If all entries at the corresponding positions are the same, then matrices are equal. Otherwise, they're different. Some examples of some interesting matrices. So we have matrix 1 by 1 containing 4 inside. Another matrix 1 by 3, so 1 row, 3 columns. This matrix C has 3 rows and 1 column, so it's 3 by 1. Matrix D has 2 rows and 2 columns, so it's 2 by 2. We also call matrices that have the same number of rows and columns square matrices, so this will be a square matrix, so matrix D will be square. Matrix E has 1, 2, 3, 4 rows and 2 columns, so its size is 4 by 2. Matrix F has 3 rows and 4 columns, so size is 3 by 4. And then I have a couple of very special matrices. In each case, the only entries are zeros. So here I have 3 by 1, so 3 rows, 1 column, all zeros. So this matrix is called zero matrix. Here I have a matrix 2 by 2 full of zeros. All entries are zeros. It's also called zero matrix. Here, matrix 2 by 3, only zeros inside, it's also called zero matrix. Matrix 1 by 4, only zeros inside, is also called zero matrix. And any m by n matrix that has only zeros as entries is called zero matrix. So when we talk about zero matrix, most of the time we will need to specify what is the size. If we want to find entries of a matrix, let's say our matrix C here, and I want to find entry 3, 1, well, that means I need to go to row 3, column 1. Entry is -1. In matrix E, I want to find entry 3, 2, so matrix E here, I need to go to the row 3 and column 2, so entries is 5. So 3, 2, entry 5. Matrix A here, I want entry 1, 1, well, it's number 4. So the entries of the matrix are numbers. F, where is F here? I want entry 2, 4. So second row, column number 4. 1, 2, 3, 4. So the number is -1. If I want from F entry 3, 3, let's say F entry 3, 3. I need to go to row 3, column 3, 5. Check. So those are important things. Entries are numbers, so these are the positions. First index tells us the row, and the second gives the column, and then we go and collect the number. Very important to remember the size of your matrix. First index tells how many rows, second how many columns. So this is read 3 by 4. Another important thing is a transpose of a matrix. So I have a matrix here, A, 3 by 4, so 3 rows, 4 columns. And this notation is read A transpose. Some people like to say transpose A, just fine, no problem at all. What is the transpose of a matrix? Well, the transpose is simply another matrix where the first row of A is set to be the first column of a new matrix. The second row of A will be the second column of a new matrix. The third row of A will be the third column of the new matrix. So the transpose is just flipping the rows and columns actually. So you take first row from A, this becomes first column of A transpose. Second row of A becomes second column of A transpose. Third row of A becomes third column of A transpose. You can also say, if you wish, first column of A becomes first row of A transpose. Perfectly correct. Okay. Second column of A becomes second row of A transpose. Perfectly correct. Third column of A becomes third row of A transpose. And fourth column of A becomes fourth row of A transpose. So you can see it in any way you like. It's just changing rows for columns or columns for rows. Obviously, if you transpose this, you're gonna get A back. So transpose of a transpose of A is A. Obviously, you realize that A and A transpose, they are not equal. This is 3 by 4 and this is 4 by 3. Already we know that they are not equal, they don't have the same size. Okay? And even if I have some matrix, let's say D, that is 2 by 2. So D transpose would be, so the first row becomes first column, the second row becomes second column. So these two matrices are both 2 by 2, but obviously they are not equal because entry 1, 2 here is 0 and entry 1, 2 here is 1. And also entry 2, 1 is 1, here entry 2, 1 is 0. So we see that D is not equal to D transpose. Another important example are these column matrices. So 3 by 1, 3 rows, 1 column. It's called sometimes column matrix. The transpose of this will be a row matrix. So just when it's sleeping is 1 row with 3 columns, so it is 1 by 3. So obviously they are not equal, they don't have the same size. Row matrix 1 by 3, only zeros inside. Transpose will be a matrix 3 by 1 with only zeros inside. So obviously again, these matrices are not equal. The size is not the same. We have some matrices that we like a lot. Square matrices, n by n. So what is a square matrix? A is said to be a square matrix if and only if A has the same number of rows and columns. So that means, for instance, matrix 1 by 1 has the same number of rows and columns, matrix 2 by 2 has the same number of rows and columns, matrix 3 by 3, 4 by 4, and in general n by n. So matrices like 7 by 7, those are square matrices. Here is one, 4 by 4. So 4 rows, 4 columns, it is a square matrix. We define a main diagonal which is defined only for square matrices. So what is that? Those are just the numbers on the diagonal. So you have this as a diagonal of your square. So this is the main diagonal. So the entries on the main diagonal are 2, 5, -1, and 4. Well, we define also something called trace of a matrix A, which is also only defined for square matrices. Trace is actually just sum of the diagonal entries. So you have your main diagonal and you add the entries. So for this matrix A here, the trace is 2 plus 5 plus -1 plus 4. So we add, and the trace is 10. For another square matrix 3 by 3, here, the trace is summation of diagonal entries. So 3, -4, and 0. So we add all that, the result is -1. So that's the trace of B. So that's just terminology actually. Another type of matrices that we like a lot are diagonal matrices. So diagonal matrix is a square matrix whose off-diagonal entries are 0. So the definition here is about off-diagonal entries. It doesn't say anything about entries on the diagonal. So the main diagonal here, what matters is that everything outside the main diagonal is 0. And then we call it diagonal matrix because everything else is 0. Now, what could be the diagonal entries? Well, they can be any real number, including 0, by the way. So this one is cute. We have the diagonal entries that are different from 0. Here also 2 by 2 matrix. But in this case, so we see that all off-diagonal entries are 0. That's good. Now, whatever the diagonal entries, we don't care. Now here we could have 0 also. It's not a problem at all. The definition talks only about off-diagonal entries. Those off-diagonal entries must be equal to 0. What is on the diagonal? Nobody cares. That means that I can have 0 matrix. This one is diagonal 1 by 1. This one also is diagonal 2 by 2. 3 by 3 is also diagonal. So pretty much any 0 matrix n by n is also a diagonal matrix. Why? Because off-diagonal entries are 0. We don't care what are the entries on the diagonal. Nobody cares. Here, just to tell you that actually we can have some ugly numbers also. So we don't need to have cute numbers only. So what matters is off-diagonal entries are 0. What is going on the diagonal doesn't matter. Other type of matrices that we have also, that we use often, is the identity matrix. Well, now identity matrix is a square matrix. It's actually a diagonal matrix, so off-diagonal entries are 0. But now the constraint is on the diagonal entries, so there need to be 1. So identity matrix has zeros off the diagonal, and on the diagonal has 1. So 1 by 1 matrix with 1 inside, that's identity. 2 by 2, we have off diagonal entries 0, and on the main diagonal we have 1. So this is 2 by 2 identity, 3 by 3 identity. So we have off diagonal entries 0, and the diagonal entries are all equal 1. So that's called identity matrix. Same thing for 4 by 4. So you have zeros off diagonal, and on the diagonal you have 1. Other types that we see often are triangular matrices. Now we have something called upper triangular matrix, which is a square matrix with zeros below the main diagonal. So it's a little bit funny, we call it upper when it has zeros below the main diagonal. Again, the definition doesn't say anything about the entries above the main diagonal, what they should be. They can be any number. And the definition doesn't say anything about the values on the main diagonal. They could be also any real numbers. What matters is that below the main diagonal we have zeros. For instance, in this matrix, we have the main diagonal 2 and 4. Below we have zeros, so this is upper triangular matrix. In this case, below the main diagonal we have 0, So this is upper triangular matrix. Okay, it is also diagonal. Happens to be, it's fine. And we will see next definition for lower, it will be this one will also be a lower. So one matrix can have several, can be classified in several categories. This one, again, 0 is below. As long as you have 0 below the main diagonal, this is upper triangular matrix. We don't care what are the values on the diagonal. We don't care what are the values above. So this means that a 0 matrix can also be upper triangular. For 3 by 3, for instance, we have the main diagonal, 7, minus 2, 1, and below we have zeros. That's what matters. We instantly classify this as upper triangular matrix. This guy here, the main diagonal, 2, 0, minus 1. Below we have zeros, so this is upper triangular. Same thing here. For 4 by 4, again we spot the main diagonal, and then below we have zeros and only zeros, so this is upper triangular. We don't care what are the values above the main diagonal, and we don't care what are the values on the diagonal. The only thing that matters is that zeros are below, and then this is classified as upper triangular matrix. Which means that 0 matrix, n by n actually, 4 by 4 or identity 4 by 4, or more generally identity n by n and 0 n by n, are all upper triangular matrices, because they satisfy the definition. Definition just says that you must have zeros below the main diagonal. If you have them, you classify as upper triangular matrix. Something similar for lower triangular matrix. It's again a square matrix with zeros, this time above the main diagonal. So in this case, we have 0 above the main diagonal, so this is lower triangular matrix. 0 above the main diagonal, lower. Okay? We don't care what is on the diagonal, we don't care what is below, only what is above. We only care what is above the main diagonal. It's 0, so this one is lower triangular matrix. In this case, 3 by 3, again, main diagonal, above all zeros, so this is lower triangular matrix. In this case, we have our main diagonal, and we have zeros above, so this is lower triangular matrix. Okay, so you can say, oh, but wait a minute, I have zeros below also. So this matrix is actually a diagonal matrix, because it has zeros off diagonal. At the same time, it is upper triangular, and at the same time, it is lower triangular. Well, good for the matrix. So you see that one matrix can be classified in several categories. It's not a problem. Again, here we have zeros above the main diagonal, so this is lower triangular matrix. Similarly, for identity n by n and 0 matrix n by n, they satisfy the definition of lower triangular matrix. So we know that identity n by n is diagonal, it is upper triangular, and it is lower triangular. 0 matrix is diagonal matrix, and it is upper triangular, and it is lower triangular. No problem at all. So one matrix can be classified in several categories. This is just to give names to special forms of matrices. Nothing else, just vocabulary actually. So one other type of matrix that is super important is symmetric matrices. So what is a symmetric matrix? It's a matrix that is square and that is equal to its transpose, which means if you shift rows and columns, you get the same matrix actually. So for instance, what this means is you swap these indices and the values are the same. So entry 1, 7 is equal to entry 7, 1. Entry 1, 2 is equal to entry 2, 1. So all these entries need to, when you swap them, the entries are the same. So when you swap the indices, entries are the same. Also, what you figure out immediately by the definition that symmetric matrix is the one which is equal to its transpose, we immediately say, hey, but a diagonal matrix it has zeros off diagonal, so obviously it is symmetric. It is obviously upper triangular and it is obviously lower triangular. So one matrix can classify in several boxes, it's not a problem. So let's see some examples of the symmetric matrices. So here I have a 3 by 3 matrix. So it needs to be square, that's the first condition. And then I check if the entry 1, 2 is equal to entry 2, 1. Entry 1, 3 is equal to entry 3, 1. Entry 2, 3 is equal to entry 3, 2. What's going on the diagonal? Nothing. Diagonal doesn't change. This one here, 4 by 4, a little bit more involved. What we see is the entries, so it's pretty much just mirror image across the diagonal. So you have entry 1, 2 is equal to entry 2, 1. Entry 1, 3 is equal to entry 3, 1. Entry 1, 4 is equal to entry 4, 1. Then I change. Entry 2, 1 is equal to entry 1, 2, we know that already. Entry 2, 2 is equal to entry 2, 2 obviously, because it's from the diagonal. So entry 2, 3 needs to be equal to entry 3, 2, well it is. Entry 2, 4 needs to be equal to entry 4, 2, well 4, 2 it is. Okay, so then we move on. Entry, obviously you see now that this guy is equal to this guy. So we go here, entry 3, 4 is equal to entry 4, 3. So that's it, diagonal doesn't change. It's just a mirror image across the diagonal. Here, for instance, in this matrix, you see the diagonal doesn't change, and then you have 1, 2 equal to 2, 1. So this is symmetric matrix. This one is also symmetric. Identities is symmetric, zero matrix is symmetric. If you have 1 by 1, well, it's equal to, it's transpose because it's the same matrix. So symmetric matrices are equal to their transpose. We need to define and perform some matrix operations. So we have matrices and we can do things with them. For instance, we can add or subtract matrices. We can multiply a matrix by a number. So this is multiplication by a scalar. Just multiply a matrix by a number. And we can multiply matrices among themselves. So I can take two matrices and multiply them together. There are rules for each of these operations. So for addition and subtraction, we can add or subtract the matrices that are having the same size. So if your matrices are of same size, then you can add them or subtract them. For instance, here I have three matrices, A, B, and C. A is 2 by 3. B is also 2 by 3. And C is 2 by 2. So the rule says you can add or subtract matrices of same size. So I can add A and B, but I cannot add A and C because A, the size of A is 2 by 3 and size of C is 2 by 2. So they don't have the same size, so I cannot add them together. The same thing for B and C. I cannot add B and C because they don't have the same size. So this addition here or subtraction is not defined. Here also I can not add nor subtract A and C because the dimensions, the size is not the same. Now, fortunately I have A and B of same size, 2 by 3 both of them. And I can add them or subtract them. So how do I do that? First thing, so was the check the size. So my resulting matrix will also be 2 by 3. So what I do is only add the number at the position 1, 1 from A with the number in the position 1, 1 of B. So I have 2 minus 1. That's what I have in the position 1, 1 of my resulting matrix. In the position 1, 2, I take entry 1, 2 from A plus entry 1, 2 from B. So I have 0 plus 4. For my resulting matrix, entry 1, 3 is obtained by adding entry 1, 3 from A with entry 1, 3 from B. So I have 4 plus minus 2. Okay. This will be also 2 by 3 matrix. Now, to fill in entry 2, 1, I take entry 2, 1 from A plus entry 2, 1 from B. So 1 plus 3. Now, to get entry 2, 2 from the resulting matrix, I take entry 2, 2 from A, so 3, plus entry 2, 2 from B, which is 0. And then for the last entry 2, 3, I take entry 2, 3 from A, minus 1, plus entry 2, 3 from B, plus 2. So now all I need to do is complete the process. 2 minus 1, 1, 1 plus 4, 0 plus 4, 4, 4 minus 2, 2. So it's going to be still 2 by 3 matrix. Then here 1 and 3 is 4, this one 3 and 0, and this one is 1. So A plus B matrix is this one. It's still 2 by 3, and the entries are actually just addition of corresponding entries in matrices A and B. And again, I cannot add A and C, I cannot subtract them either, because they don't have the same size. I cannot add or subtract B and C because they don't have the same size. For our pleasure, we can also subtract matrices. I can subtract A minus B or B minus A or something else. We will see later different games we can play with matrices. So let's say now I want to subtract A and B. So the entry 1, 1 will be entry 1, 1 from A minus the entry 1, 1 from B. So minus minus 1. And then entry 1, 2 from A minus entry 1, 2 from B, and then entry 1, 3 from A minus entry 1, 3 from B. Good. So now entry 2, 1, so 1 minus 3, and then 3 minus 0, and minus 1 minus 2. So this is still 2 by 3. It's going to be squeezed a little bit. So 2 minus minus 1, so this is 3. This is minus 4, 6, and then minus 2, 3, minus 3. So this is still 2 by 3. Obviously, A minus B is different from A plus B most of the time. So that's how we do addition and subtraction. We simply add corresponding entries or subtract corresponding entries. For scalar multiplication, it's super easy. So if I have m by n matrix and I multiply by any real number, all I do is multiply each single entry by the same number. So it's not a big deal. So if I multiply this matrix by 2, so I have 2 times 4, and then 2 times 1, and then 2 times 2, and then the row 2 is 2 times 0, 2 times 3, and 2 times 1. So I multiply every single entry by 2, so I get the result 8, 2, 4, 0, 6, 0, 2. So this is still 2 by 3 as original. So all I did is just multiply every single entry by the same constant. So now we can have something more involved. I have 3 matrices A, B, C. All of them are 3 by 2. Right? 3 rows and 2 columns, all of them. So I can actually add them and subtract them. Just to make sure. So let's say I want to compute a matrix D that is actually 2 times A minus 4 times B plus 5 times C. Let's have fun. So you have several ways of doing it. One of the ways is simply do one step at a time. So you multiply 2 times A. So you multiply every single entry of A by 2. So this is what you get. Then minus, and then multiply every single entry of B by 4, because I kept the minus outside. So I multiply every single entry of B by 4. Multiplication finished. Plus, and then multiply every single entry of C by 5. 5C, this is it. Now I just proceed adding corresponding entries. So 6 minus 4, it is 2, plus 0, so that's 2. Then the entry 1, 2. 4 minus 4, so this is plus 4, so 4 plus 4 is 8, plus 10, 18. Good. Now 2 minus 0, 2, plus minus 10, so 2 minus 10, minus 8. Entry 2, 2, 0 minus 8, negative 8, plus 15, so that's 7. Last row 0 minus 24, so that's negative 24, plus 5, so that's negative 19. And the last entry 3, 2, so 2 minus 16 is negative 14, plus 20, that's 6. This is still 3 by 2. So that's what we normally do. We can proceed one step at a time, or if you are more practiced, you can compute this a little bit faster if you wish. Make sure you don't make any errors in computation. But the idea with addition and subtraction is just you add or subtract the corresponding entries. When you multiply a matrix by a scalar, you multiply the single entry of the matrix by the same number. So those are relatively easy things. Now the last operation is matrix multiplication, and this one we need to be a little bit more careful. First thing to realize is that if I want to multiply two matrices A and B, I can do it if and only if the inside dimension fit. So here I have matrix M by N, and B is N by L. So M can be any whole number, and L also, doesn't matter. What matters is that N are the same values. Otherwise I cannot do the product. So that's why this is super important, that inside dimensions must be equal. The resulting matrix of the product will be matrix C with dimensions M by L. And we will see how to compute it. I just want to make sure you really understand what's going on. I can make the product of two matrices if and only if the inside dimensions fit. They are the same. So here I have 3 by 4 matrix times 4 by 2 matrix. That's good because 4 and 4 inside dimensions are equal. 4 by 2 times another matrix 2 by 6. Good, because inside dimensions are the same, 2 and 2. So the resulting matrix here will be a matrix C, dimensions or size 4 by 6. What matters is that the inside dimensions fit. So another example, I have 6 by 3, and I can multiply by a 3 by 2, for instance, because the inside dimensions fit, they are equal. The resulting matrix will be matrix C of size 6 by 2. Some examples where we cannot do the multiplication of matrices. For instance, a matrix 3 by 4, I cannot multiply it by a matrix 3 by 2. Why? It's because the inside dimensions are not equal. 4 is not equal to 3. So this product is not defined. I will not be able to do that. So whenever you have something but the inside dimensions are not equal, the product is not defined. It's impossible to do. Another example, a matrix 4 by 6, I try to multiply by a matrix 3 by 6. It doesn't work because the inside dimensions are different, they are not equal. So this product is not defined, impossible to do. A matrix 1 by 3 cannot be multiplied by a matrix 2 by 3. The reason, inside dimensions are not equal. So this product is not defined, cannot be done. So we cannot just multiply any matrices we like, only those for whom the inside dimensions are equal. So let's see how it works. So I'm here with a matrix A 2 by 3 and a matrix B 3 by 4. I check first if I have the inside dimension that are equal. Yes, I do. 2 by 3 and 3 by 4 inside dimensions are equal, so I can proceed. I can do the product now. The resulting matrix C will be of size 2 by 4. So now we will learn how to do it properly. You can see this as actually performing a dot product between rows and columns. So rows of A dot product with columns of B. So that's one way of seeing it. So entry, so 1, 1. So the idea is pretty much to fill in the matrix here. So I know that this matrix will have 2 rows and 4 columns. So I would like to fill each entry one at a time. So to fill entry 1, 1 of the new matrix, product matrix, I need to take row 1 from A, dot product column 1 of B. So that's what we are doing actually. So I'll write it in detail. So I have 2 times minus 1 plus 0 times 0 plus minus 1 times minus 3. So that will be my first entry of the resulting matrix. So it's row 1 of A times column dot product with column 1 of B. So that's entry 1, 1 of the resulting matrix. Entry 1, 2 will be row 1 from A dot product with column 2 from B. So I'll have 2, 2 plus 0 times 4 plus minus 1 times minus 1. So it was row 1 from A dot product with column 2 from B. So that's entry 1, 2. Entry 1, 3 will be row 1 from A dot product column 3 from B. It will be 2 times 5 plus 0 times 0 plus minus 1 times 2. Now the last entry here, so when entry 1, 4 will be row 1 from A dot product with column 4 from B. So it's 2 times minus 2 plus 0 times 1 plus negative 1 times negative 4. So that's how I fill the first row. Now let's fill the second row. So entry 2, 1 will be row 2 from A dot product with column 1 from B. So row 2, 1 times negative 1 plus 3 times 0 plus 1 times negative 3. So that's entry 2, 1. So we took second row of A dot product first column of B. Entry 2, 2 will be second row of A dot product with second column of B. So it is 1 times 2 plus 3 times 4 plus 1 times negative 1. Entry 2, 3 will be second row, so row 2 from A dot product with column 3 from B. So that is 1 times 5 plus 3 times 0 plus 1 times 2. And the entry 2, 4 will be row 2 from A, dot product, column 4 from B. So it will be 1 times negative 2, plus 3 times 1, plus 1 times negative 4. So you see I have 2 rows and 4 columns. Okay, let's compute this to see what's going on. So I have negative 2 plus 0 plus 3, so that's 1. Then this guy is 4 plus 0 plus 1, so that's 5. And this guy is 10 plus 0 minus 2, so that's 8. The last guy, 1, 4, is negative 4 plus 0 plus 4, that's 0. Entry 2, 1, negative 1 plus 0, negative 3, so that's negative 4. Entry 2, 2, I have 2 plus 12, that's 14, minus 1, that's 13. Entry 2, 3, 5 plus 0 plus 2, that's 7. The last piece, negative 2 plus 3, that's 1, minus 4, that's minus 3. Again, this is 2 by 4. So the matrix C, the product of A and B, is this matrix here. How will we get it? By doing the dot product of rows with corresponding columns. So row 1, column 1 gives us entry 1, 1. Entry 1, 2 is obtained by row 1 dot product column 2. So order of matrices is important. So that's something that we are going to see very quickly. By the way, we see that B times A is not defined. So B is 3 by 4 and A is 2 by 3. So we see that we have a problem. They are different, so this doesn't work. So immediately we see that A times B is not equal to B times A. So we cannot swap order of multiplication. That's something that is super important to notice. Order of multiplication cannot be changed. Because you see, A times B gives us this matrix, but B times A is not even defined. I cannot even perform the operation. So obviously, in general, A times B is different from B times A. Be very careful. This is one of the properties that we need to remember. Let's compute some more matrix products to see what happens. So here I have a 3 by 2 matrix and 1 by 3 matrix, A and B. So obviously I see that I cannot do the product AB because A is 3 by 2 and B is 1 by 3. So inside dimensions are not equal. Therefore this product is not defined and cannot be performed. Let's see if I can do B times A. Well, B is 1 by 3 and A is 3 by 2. Well, that's great because these two inside dimensions are equal, so I can perform the product. So how does it work? Well, I need to take row 1 from B and then do the dot product with the column 1 of A to compute entry 1, 1. So let's take row 1 from B, dot product with column 1 from A, and get the entry 1, 1. So 1 times 2 plus 2 times 1 plus 0 times 2. That's entry 1, 1. For entry 1, 2, I need to take row 1 from B, dot product with column 2 from A, because I'm doing product B times A. 1 times 3 plus 2 times 0 plus 0 times 1. Right? So this is equal to, this is 2 plus 2, 4 plus 0, so this is still 2, 4, 3 plus 0 plus 0, so that's 3, so this is 1 by 2, well that's what I expected, the dimension of the resulting matrix is 1 by 2. Obviously we see again that A times B is not equal to B times A. You cannot swap order for multiplication of matrices. Order of multiplication for matrices is super important. You cannot swap it. You cannot swap the matrices. Impossible. So another example, let's say how we do the product AB. So I need to fill in, so these are 2 by 2 matrices. So the resulting matrix will be 2 by 2. So I take first row of A dot product with first column of B. So 1 times 4 plus 2 times minus 2. Entry 1, 2 is first row of A dot product with second column of B. 1 times minus 6 plus 2 times 3. Entry 2, 1 is row 2, second row from A dot product first column of B. 2 times 4 plus 4 times minus 2. Entry 2, 2 for row 2 from A dot product with column 2 from B. 2 times minus 6 plus 4 times 3. So if we compute this, so we have 4 minus 4, 0. Minus 6 plus 6, 0. 8 minus 8, 0. Minus 12 plus 12, 0. So the resulting matrix is 0 matrix 2 by 2. So A times B in this case is equal to 0 matrix. We notice that A is not as equal to 0 matrix and B is not equal to 0 matrix. Yet the product AB is equal to 0 matrix. Okay, so this is very important observation. We can have two non-zero matrices whose product is equal to a 0 matrix. And that's fine, there's nothing wrong with that. Okay, so whenever you see product of two matrices equals 0, well, they could be non-zero matrices also. You don't know, you cannot conclude from the fact that the product is equal to 0 matrix that one of the matrices is 0. No, that's not true. We have an example here. This is not 0 matrix, this is not 0 matrix, yet their product is 0 matrix. Be careful. Since these matrices are 2 by 2, we can also perform product BA. So entry 1, 1 is first row of A dot product with first column, first row of B dot product first column of A. So 4 times 1 minus 6 times 2. Then entry 1, 2 will be first row of B, second column of A. So 4 times 2 minus 6 times 4. Entry 2, 1, row 2 from B, dot product, column 1 from A. So minus 2 times 1 plus 3 times 2. Entry 2, 2 of the product will be A, row 2 from B, dot product, column 2 from A. So minus 2 times 2 plus 3 times 4. This thing is equal to 4 minus 12 minus 8. And here 8 minus 24, that's minus 16. This guy, 2 plus 6, negative 2 plus 6, negative 4. Negative 4 plus 12, 8. Okay. And this is a 2 by 2 matrix. So again, we see that B times A is not equal to A times B. Okay, so we need to be careful with these things, because if we make a mistake, then everything is wrong. Okay, so make sure that you understand that even though the product of two matrices could be zero, it can happen that none of them is zero actually. A and B are different from zero, that's fine. So let's see here, what can we do with AB? So I'll put just fast, 1 times 2 is 2, plus 6 is 8, 1 plus 4 is 5, then entry here 2, 1, 4, plus 12, 16, 2 plus 8, 10, ta-da, finished. AC, so first row, first column, minus 2 plus 10, 8. Then first row, second column, 7 minus 2 is 5. Second row, first column, minus 4 plus 20, so that's 16. And then 2, 14, minus 4 is 10. So we see that AB, in this case, is equal to AC. They're equal. But B and C are not equal. So this is different from what we have with real numbers. You can have AB equal to AC, yet matrices B and C are different from each other. So be careful, you cannot make any conclusions. Another example of a multiplication. So let's say here I have three matrices. So I have 3 by 2, 2 by 1, and 1 by 4, and I need to do the product. So I can decide to start with these two, copy this one, and continue. Or I can decide to copy this and do the product of these two. It's up to me, whatever I choose, the result will be the same. So you choose whatever you want. Do you want to do the product of the first two and copy the third, and then when you get the resulting matrix, do the product of the remaining two pieces? Or you copy the first and do the product of the second and third, and the result will be multiplied by this matrix. It's up to you what you want to do. So the result will be the same. So I'm going to multiply these two. So the resulting matrix, so I have inside dimensions are equal, so the resulting matrix here will be 3 by 1. So I know that. So 0 times minus 4 plus 2, minus 4 plus 4 is 0, minus 1 times minus 4 is 4, plus 1 is 5. So this is 3 by 1 matrix from the product of these two. And then I copy the other guy. Oops. So this one is 1 by 4. And again, inside dimensions fit, so that's good. So my resulting matrix will be 3 by 4. So let's prepare for that. So what do I do? First row, first column. So this is 4. 0. 2 times 1 is 2. 2 times minus 1, minus 2. And 0 times 2 is 0. 0 times 0 is 0. 0 times 1 is 0. 0 times minus 1 is 0. Last one, 5 times 2 is 10. 5 times 0 is 0. 5 minus 5. This is a 3 by 4 matrix. You will get the same result if you copied this, did the product of these two, and then multiplied this with the result. You will get the same thing. Another example. I have three matrices, all 2 by 2, 3 by 2, and 1 by 3. And I need to compute A times B transpose times C transpose. Wow, okay, so A, let's copy A, 2 minus 2, 1 minus 4. B transpose, so it's transpose of this one. So this one was 3 by 2, the transpose is 2 by 3. Okay, so first row becomes first column, second row becomes second column, and third row becomes third column. Okay, so this one was 2 by 2, so this one is 2 by 3. And C transpose, so this is 1 by 3, the transpose will be 3 by 1. So just this row becomes a column. Okay. So for fun, I'm just gonna do the opposite from what I did. I'll copy the first one, and I'll do the product of the other two, and then see what happens. So obviously these two are equal inside dimension, so I can do the product. The result will be a matrix that is 2 by 1. So let's go. First row times the first column. So 0 minus 2 plus 0. So that's minus 2. Then second row column, 0 times 0, 0. 2 times minus 2, minus 4. Minus 1 times 1, minus 1. So minus 4 minus 1 is minus 5. So obviously again, inner dimension are equal, so that's fine. So now my resulting matrix will be 2 by 1 again. So do the product, minus 4 plus 10, so that's 6, minus 2 plus 20, so that's 18, so 2 by 1. Okay, very nice. We could maybe, what happens if I compute A square? What is A square? Is A times A. Well, since A is square matrix, I can do that. So A squared is A times A. A to the power 3 is A times A times A. So let's see what happens. So just apply the definition of multiplication of two matrices, nothing else. These are 2 by 2, so the result will be 2 by 2. 2 minus 2, 0, okay. Minus 4 plus 8, that's 4. 2 minus 4 is minus 2. The last one, minus 2, 16. So A squared is this matrix. A to the power 3 is A times A times A, which is A squared times A, which is also equal to A times A squared, doesn't matter. So here I have A squared, so A3 will be A squared times A. So since I have A squared, I'll use it just to see what happens. And A was 2, negative 2, 1, negative 4. Again, the product will be 2 by 2 matrix, so 0, 4, 0, minus 16, minus 4, plus 14, so that's 10, 4, minus 56, minus 52. Okay, so that's how we compute the powers of matrices.